over here. Oh, it was class detail that mentioned too, so which was you guys. So for today, Wednesday, October 6th, you guys know we're near the end of the graded quarter, right? So I have to get my grades in this weekend, this 3-day weekend coming up. And so here's the story. I know you guys have just turned in your quizzes. I got those graded. I'm still waiting for a few more quizzes, and once I get the last few in, then I can post the solutions, which I also have ready. All I have to do is press a button, and then I'll get you guys your quizzes back. And I have to give you guys opportunity to do corrections last couple quizzes. So let's keep doing that. I think it's a pretty good idea too. But there's this whole sequence of events, right? So probably the grading period is going to run out before you guys get your quizzes back, just because this whole sequence of events. So and some of you guys have might just take a point or two to get the next letter grade. So here's what we do. Do you guys remember A offered you guys a bonus homework for forces, chapter 4? Yeah, so the bonus homework. Now, some of you guys already turned that in, and if you did, then what I did is I went back in the grade book and I changed it from 20 out of 20 to 20 out of 10. So if you already turned it in, then that boosted your grade, well, 10 class points, so move your class grade up about a point or two. If you still want to take advantage of this and you do that, then you can turn it into me the next few days, and I'll give you guys those points too. All right, so you guys just saw these Kepler's laws of planetary motion. Well, you saw Carl Sagan explain the first two. So planets don't actually move in circles around the stars. They actually move in ellipses, and that probably makes sense why, if you remember from yesterday's notes, because a circular orbit, which you can calculate with this. Remember, this is a fragile situation because if this were to slow down, anything in circular orbit, like true circular orbit, were to slow down like any bit for any reason, then, well, it would no longer be able to stay in orbit. It would spiral down and crash. Okay? Now, if you go a little bit faster, you get into an elliptical shape, which actually is pretty stable, because let's say like Jupiter swings by, throws off your orbit a little bit, speed up, slow down. Okay? Well, that's okay because you can adjust a little bit and still stay in an elliptical orbit. Okay? If you speed up faster, you eventually reach escape speed. And do you guys, did I tell you guys yesterday what shape that would be? Let's say you're passing by a planet and you're going faster than this value. Maybe the planet's going to bend your motion, but what shape would that take? Does anybody know? It's definitely not a circle. It's not an ellipse either because the ellipse would curve back on itself. But if you're going faster than that, not a parabola. Oh, that'd be a good guess. But hang on to the idea because I talked about that too. So hang on to the idea. I'll sweep back and talk about that. Oh, where'd my protractor go? Oh, here it is. So, you guys got some string on your desk? Okay. About to have you guys do an activity with the string. So this here ellipse, remember how Kepler figured out that these orbits were elliptical? He was crunching a bunch of data, like astronomical data that had been collected over many years. And the difference between the elliptical shape and the circular shape is, well, where are the planets in the sky? You guys know what 1 degree is, right? So on this protractor, 1 degree is just one little tick mark, like 1 degree, right? And then, according to the story you guys just heard, if you split 1 degree into 60 parts, each one of those parts would be a minute, and the location of the planets in the sky were off by only about 8 minutes. So 8/60ths of a single degree, right? That was enough to say that, okay, well, it can't be circular, and then you eventually figure out that's this elliptical shape. Right? Kepler's second law says that is the equal area for equal times rule. So suppose it takes a planet like 30 days to go from here to here. Well, when the planet's closer to the star, 30 days, it's going a little faster, so it might sweep out an area that looks like that. And those areas are equal for equal times. Now, it's one reason it's really amazing that Kepler was able to figure out the second law of planetary motion is because this is sort of an integral calculus type thought approach. But this is all before Isaac Newton even comes along. He was able to figure out those areas the same. Kepler's third law of planetary motion relates the time period to how far its average distance from the star. So the square of the time period is directly proportional to the cube of the distance to the star. So that's as much as Kepler figured out. Like this relationship here. Now, if you add on Newtonian physics to that, the whole like GMM over R squared, and then combine everything together, you can actually get a modified version of Kepler's third law, which says this: the time period for a planet to go around, so for Earth that would be 365 days, is equal to this right here, where this R represents the distance to the star. So for Earth, it's like 150 billion meters, I think, something like that. Okay. All right. So this string right here, tie the string in a loop. You guys got a good loop of string right there? Good loop of string? Find some paper. Throw down this loop. Now, I'm going to use 3 pens to do this. You just need at least 1 pen or pencil to write with, and then maybe a couple places to like place markers. Okay. I'm going to throw down a couple of markers, so like here and here. Okay. And then take the 3rd pen and go all the way around with this. Hey, so what shape is that right there? It's not a circle. No, that's not a circle. That is an ellipse. Yeah. Yeah. It would be a circle if these 2 points were what?
The same point.
Exactly, yeah. If you move these 2 points on top of each other, that would be a perfect circle, wouldn't it? Yeah. So a circle is actually a special case of an ellipse, kind of like a square is a special case of a rectangle, right? Is that true? Right. This could represent, say, the orbit of Earth, where the sun would be centered at one of these. Ooh, what are these 2 points called? Oh. Right, so you throw down a couple of pins.
Yes.
Let me do this again. These are the focal points, right? The focal points. Okay. So throw down a couple of pins to represent the focal points of an ellipse. Okay. And then you're using this string as a constraint. See how that string is triangular? Triangular string. It's always triangular, isn't it? The string is always going to be a triangle. Well, unless it's like flat like that, but it's always a triangle. That string is going to constrain the motion of what's drawn with E. Yeah, that'll create an elliptical shape. The further apart these focal points are, the more elongated the shape will be. It'll be more obviously an ellipse and less a circle. Okay. Let's talk about the geometry of an ellipse a little bit. Maybe compared to circles. So, guys, what's the area of a circle? Pi r squared. Yeah, pi r squared, right? What's the circumference of a circle? 2 pi r. Okay. Sometimes students mix up these two, but you guys know r squared. That's like square feet, square meters. That would refer to an area versus a linear relationship which takes some distance in like meters or feet. Okay. How about an ellipse, though? Well, if I have this line that goes along this axis that goes through the 2 focal points, okay, and they go perpendicular to that, like right through the middle, like that. Okay. You guys see this wedge right here? Or they just hashed in. Now this might have sides I might call A and B. Okay. Now for a circle, those would just be the same, wouldn't they? Just be R and R. And then, the area of a circle would just be pi times this wedge, pi r squared. That's what that would be for a circle, right? But for an ellipse, A and B are different. So what's the area of an ellipse? You guys have a guess? How many guys are thinking it's probably pi AB? Area of an ellipse is pi AB, right? That makes sense. Right. So this wedge multiplied by, that wedge times 4, but A times B is a big old rectangle. That times pi would be the area of an ellipse. Right. So to finish this off, what is the perimeter of an ellipse equal to? What's the perimeter of an ellipse? You know what? The greatest minds in all of mathematics have never been able to figure out exactly the perimeter of an ellipse. This is an open question. There are some pretty close approximations. There might be a formula in your math textbook, but nobody actually knows. Nobody's actually been able to figure that out. Right. Let's go back to back to these shapes then. So you can have a circular orbit as the as a circle. If you go into an ellipse, it's more stable. That's what planets actually do around the stars. That's what's been observed. If you hit escape speed, sorry, one more thing I want to say about ellipses. So for planets, they're pretty close to circles, but they're not exactly circles, they're ellipses. If you look at comets, comets have extremely elongated elliptical paths, right? Actually, that was one thing I told you guys led to this entire class being founded. You guys remember that back in the 18th century, or no, 17th century, everyone was looking at the sky at Halley's Comet. It wasn't called Halley's Comet at the time, but a guy named Halley went and talked to Isaac Newton. You're trying to figure out the motion of this thing. Right? That's what led to physics and calculus being published. And then if you go faster than escape speed, say you're whizzed by a planet, go faster than escape speed, you guys say that that's a hyperbolic shape, hyperbola? I want to tell you guys a story because there's some recent recent news in physics. You guys know that astronomers are keeping track of like thousands of asteroids, right? Especially to make sure like which ones are headed away could possibly run into Earth, that sort of thing. So scientists have tracked thousands and thousands of asteroids. They're all kind of spherical shaped. They all follow, a little bit elliptical orbits around the sun, that whole deal. But in 2017, for the first time ever, astronomers were, so they're looking at the sky, looking for different things. Okay, hey, we just discovered something new, never seen this before. They started to track its motion, and they realized that for the first time ever, they've discovered something that actually does not have an elliptical shape around the sun. It actually has a hyperbolic orbit. Well, actually, it wouldn't even be an orbit. It just it would follow a hyperbolic curve, I should say. And what that means, if this is like the sun, and we're watching some little dot, and it's okay, so where's this path? And then we measure it all out. It's like, oh, it's actually part of a hyperbola. What does that mean? Where did this object come from? Oh, yeah.
Was this the thing from Interstellar Space that was like the long, like sphere thing with like the long Hawaiian name?
Yeah, with the Hawaiian name. Yeah, Warner knows exactly what I'm talking about. Does anybody know that Hawaiian name? Yeah, Warner knows. It's
OU.
Yeah, Oumuamua. Yeah, so this special object has a name. Yeah, it has a Hawaiian name probably because it was discovered on a Hawaiian telescope originally. Yeah. This is from some other solar system. It's the first time, the only time that something's been seen, confirmed from outside our solar system to pass by. Right? But you know what? That wasn't the only weird thing about it. Not just that it was from some other solar system. That a little bit of a mystery. Remember? Yeah, Paul?
Can you show the other side of the paper real quick?
Yeah.
Okay.
Yeah. All right. So, not only was it from interstellar space, but remember how thousands of asteroids scientists have tracked, they're all kind of circulars, right? Well, this one had a weird light curve. So it was like it would get bright, dim, bright, dim, bright, dim, and would do that periodically, which is maybe evidence that it probably was not actually spherical shape. A lot of artist renditions show it kind of like a log shape, which is possible. The idea being if it's tumbling through space, that sometimes like this much faces Earth, and sometimes it's like the full length of it, right? And so then that would account for light reflections being differently. But nobody knows. That's just one hypothesis. There's another hypothesis. Maybe it's maybe a big flat piece of foil, like a solar sail, that kind of deal. That would help explain the light differences. But nothing's ever really been seen like that either. So that's two weird things. But you know what? There's actually a third weird thing about this. So already it's two anomalies. It's from interstellar space. It has these weird light curves where if you look at light as a function of time, so like light as a function of time, it's doing like shung, shung, shung. But the third weird thing is astronomers can know exactly where it should be. Like once they got its hyperbolic path marked, they say, okay, well, we can predict it should go exactly along this hyperbolic curve. They can use pretty much the physics we've been using in the class, except they use a more advanced version that's Newtonian general relativity. What we're doing in class is just an approximation of that. Right? But this object actually did not follow exactly along the path that it should have. It actually went a little bit off path like this. And there's speculation as to why. There's some good hypotheses, but nobody knows exactly why. possibly something to do with the solar radiation, pushing maybe like a cosmic solar wind. Maybe this thing is, this is one reason that this thing might be like a big old like piece of foil type shape, is because that would help explain that too. But yeah, there's a lot of mysteries about that, but it's a fun one to think about. Today, with that. All right. So yesterday, you guys remember yesterday in class, one of the last things I talked about was this hollow planet. So we're exploring the we're exploring the galaxy, come across this planet. We start to dig down and we realize pretty quickly, oh, this is an eggshell planet. Okay? And then what I was telling you guys, the story was that you could walk around on the outside perfectly normally. I mean, you might be really light because the master planet would be very small because it's just an eggshell. But the net effect is that you could apply this GMM over R squared, get your weight. You'd have a weight. You could walk around perfectly fine. But once you go inside this eggshell, remember I was showing you guys it would be a gravity-free zone all inside? Well, I picked one point to show you that would be true for one point, but that's true. It's true everywhere inside. It's a gravity-free zone. Okay. Now we're going to take this and we're going to build on this idea, because what this means is that if you we're about to tunnel down into a solid planet and say, well, what's going to happen if you tunnel into a solid planet? Okay. So what this means is that if you were to tunnel into a solid planet, anything that's below you in elevation, this applies, GMM over R squared. Anything that's below you in elevation. But anything that's above you in elevation, well, couldn't you treat that like maybe like a series of shells, right? So if you went to a solid planet, so I've got a solid planet, got my shovel, gonna do journey to the center of the earth type deal. Suppose I dig in this spiral staircase all the way down to the center. Let's say it's not molten and all that, so it's just like a solid planet. Okay? If I'm like halfway down, could you say like, well, here's a shell planet above me. Here's a shell planet above me. Here's a shell planet above me. Isn't everything above you in elevation effectively a bunch of concentric shells? So wouldn't the gravity all cancel out? You sure would. And then the only gravity force that would act on you is whatever's beneath you in elevation. And so everything beneath that dashed line there, right? That makes sense? Hey, I wonder if we could do a graph to get a big picture of what is your gravity force as a function of your distance to the center. I have a few more details here. So this planet might have radial value capital R. I'll use lowercase r as a variable radial distance, and we'll take off a rocket at some point. We'll tunnel down to the center. Actually, a good question might be, what would your weight at the very center of a planet be? And we're going to plot it all on this pair of axes of what is your weight, like gravity force and newtons. Right? So scale reading. So you brought a scale along with you. You're going to stand on the scale at various points. As a function of your radial distance from the center of the planet. Okay? So you could be at the center. That's what this would be. So some number like meters, kilometers. Right? And actually, there is a very special location, which is right at the surface. So I'll call that capital R. Okay? So we'll get a graph going for your weight for any general planet, and this could apply to any general solid planet. Actually, there is one life experience that we all have in this class, and that's just being at the surface of a planet. Probably all of us have spent our entire lives at the surface of a planet. So we know that. We know that you have a weight like mg at the surface. But the more, your new way of thinking of it is GMM over R squared. Notice I'm using capital R because special location at the surface. You could just call it mg, lowercase g if you want. Okay, and that would be right here. Okay. So at the surface, you have some weight. Okay, so that's all good. All right. Oh, one of the questions that I just threw at you guys a minute ago was, well, what if you tunnel all the way down to a spiral staircase all the way down to the center? So right at the center, what do you think you weigh? I'll throw you guys two options. At the center, you either weigh a lot less than at the surface or a lot more than at the surface. Let me see show of hands what you guys are thinking. How many guys think that at the center, you weigh a lot less than at the surface? A lot less. Yeah. All right, there's the winners right there. You guys are right. You would, in fact, you know what? You wouldn't just weigh a lot less. You would weigh how much? Nothing, right? You weigh zero. So at the center, you have zero weight. Why would that be? Let me go back and recap that because a lot of students think the opposite or struggle with this concept. So here's the idea. If you're at the surface, yeah, you can say that the force gravity on you is GMM over R squared. And I walked you guys through yesterday the idea that we're assuming the entire mass of the planet is located at its center, and then the distance from you and that point would be the radius of the planet, all that. Okay, so that's your weighted surface. Okay. But really, it's an aggregate effect, isn't it? Of the mass of the planet is spread out over its entire volume. Here's a bunch of sand grains all over the place. And some of those are pulling you to your right, some of them are pulling you to your left, and the right and left part cancel out, but everything's pulling you down. Isn't everything pulling you down? Right, so that's why your weight pulls you straight down. You're being held down in your chair. Right. But what about when you get to the center? Let's say we find like an open cave right at the center. Right. Well, where would you even put the scale down on the floor to stand on it? Right? There would be no floor to stand on. Right? Where is down? There is no down. You'd be floating around like an astronaut. Right? And think about every single grain of sand, distributed over the entire volume of the planet. Some of it's pulling you this way, some this way, some this way. This way, right? Doesn't all balance out? Sure does. That's why you feel like zero weight there. Okay. The next part of the graph we're going to do is let's do a part that you definitely should be able to do. Let's take off in this rocket. So as you get further and further away from the Earth, how is this graph going to look like as you get further and further away? Is it going to tend towards zero? But so there's probably going to be a horizontal asymptote at 0 newtons. Right? So if you get far enough away, it's going to make a horizontal asymptote at 0 newtons. So it's going to approach this dash horizontal asymptote. Right? How's it going to do that? Can you guys make a graph before I do? Or do you guys think it's going to be an inverse square relationship? Right? So this force is proportional to 1 over the distance squared. That would follow this, wouldn't it? GMM over R squared. Actually, that's exactly the equation. But, okay. Guys get that? GMM over R squared. And 1 over R squared takes that kick shape. Okay. All right, now the tricky part. Okay, so take the shovel and tunnel the spiral staircase all the way down to the center. Now, at the center, you have 0 weight. And at the surface, you have this weight. So what relationship is going to connect those dots? How many of you guys think it's going to be a straight line? Who thinks it's going to be a straight line? Straight line. I'm going to draw a straight line. Now, this would be true for the case of uniform density. So if you assume uniform density dirt all the way to the center, it would be actually one of your textbook questions. I forget if I assigned it on the main homework or the bonus homework, but I'll cover it in class if I have time because I really like this question. It says basically prove that this is a straight line relationship. Okay. So for now, I'm throwing this idea at you. We might prove this in class one day. You guys good so far? Okay. All right, let's do this.